Today is the audio visualized recording for the physical chemistry from the book Pardeep Publications, whose writer is Dr. S.C. Khetrapal. My topic is thermodynamics. Work function Helmholtz free energy and Gibbs function gives free energy. In addition to the various thermodynamic quantities like internal energy U, work, heat, enthalpy, entropy discussed earlier, two more thermodynamic quantities used were frequently in the study of chemical thermodynamics are work function and Gibbs free energy. These are briefly discussed below. Work function. This is usually denoted by the symbol A from the German word Arabi, which means work. It is defined by this equation A is equals to U minus Ts, where U is the internal energy of the system and T is the temperature of the S is the entropy. Since U, T and S are the functions of the state of system only and do not depend upon its previous history, therefore A must be state function. In order to understand the physical significance of work function, consider an isothermal change taking place at temperature T. Then A1 is equals to U1 minus Ts1 for the initial state and A2 is equals to U2 minus Ts2 for the final state, where A1, U1 and S1 are respectively the values of work function, internal energy and entropy of the system in the initial state, and A2, U2 and S2 are the correspondence value in the final state. Increasing the values are A2 minus A1 is equals to U2 minus Ts1 minus U1 Ts1 is equals to U2 minus U1 minus Ts2 minus S1. Delta is equals to delta U minus T delta S. Delta U is equals to U2 minus U1 of the system is the change in internal energy of the system, and delta S is equals to S2 minus S1 is the change in the entropy of the system. Now, according to the definition of entropy change, we know that delta S is equals to Q reversible upon T. Further, according to the first law of thermodynamics as applied to isothermal reversible process, we have minus sign before W has been used to indicate that the work has been done by the system during the change of consideration. Putting the value of delta S and delta U from equation 5 and 6 in the equation 4, we get delta A is equals to W max. Thus, for the processing occur for the constant temperature, the decrease in the work function A is equals to the maximum work done by the system. In fact, it is for the reason that is thermodynamic quantity has been termed as work function, although at one time it was called Helmholtz free energy. Gives free energy. This is usually denoted by G and defined by G is equals to H minus Ts, where H and T and S are the heat content, enthalpy, temperature, and entropy of the system respectively. As before, since H, T, and S are the function of state, therefore G is the function of state system only. Hence, for the isothermal process occurring at temperature T, we can write G1 is equals to H minus Ts1 for the initial state, and G2 is equals to H2 minus Ts2. G2 minus G1 is equals to H2 minus Ts2 minus H1 minus Ts1. H2 minus H1 minus T S2 minus S1. Delta G is equals to delta H minus T delta S. Delta G is equals to G2 minus G1 is the change in Gibbs free energy of the system, and delta H is equals to H2 minus H1 is the enthalpy change of the system, and delta S is equals to S2 minus S1 is the entropy change of the system. The physical significance of Gibbs free energy may be follows. At constant temperature, delta S is equals to Q reversible T. T delta S is equals to Q reversible. At constant pressure, delta H is equals to U plus P delta V by definition of enthalpy change. Substituting the value of T delta S and delta H from the equation 12 and 13 is the equation delta G is equals to delta U plus P delta V minus Q reversible is equals to delta U minus Q reversible plus P delta V. Now, according to the first law of thermodynamics, delta U is equals to Q reversible minus W max. Minus sign before W indicate that the work is done by the system. Delta U is equals to Q reversible delta H is equals to delta U minus P delta V. Substituting the value of T delta S and delta H from equation 12 and 13, equation 11, delta G is equals to delta U plus P delta V minus Q reversible delta U minus Q reversible plus P delta V. Now, according to the first law of thermodynamics, delta U is equals to Q reversible minus W max. Minus sign before the indicate that the work is done by the system, or delta U minus Q reversible is equals to W max. Substituting the equation, we get delta G is equals to minus W max, but P delta V is the works of expansion done by the system correspond due to an increase in value delta V. Hence, W max minus P delta, we stand for the maximum energy other than the work of expansion. This is called the maximum net work available for the from the process work done, the work of expansion. This is called the temperature and constant pressure. The decrease in Gibbs free energy is also equal to maximum net work obtaining from the process, that is the total work minus the pressure volume work of the work of expansion. It is because the change in it is measurable that useful work done has g has been the free energy. It may be further mentioned here that is the customary to refer Gibbs free energy simply as free energy. The design Gibbs free energy is only necessary for clarity. Variation of Helmholtz function work function with the temperature and volume. The work function is given by equation is A is equals to U minus Ts. Completion differentiation of equation gives dA is equals to du minus Tds minus S dt. By definition of the entropy change, we know that ds is equals to delta q reversible upon T. Further, from first law of thermodynamics, we have delta q reversible is equals to du minus dw. If the work is restricted to the work of expansion only, delta w is equals to p dv. Putting the value of 4, we have delta q reversible is equals to du plus p dv. Putting the value of 3, ds is equals to du plus p dv upon T. Tds is equals to du plus p dv. Putting the equation to both, dA is equals to du minus p dv minus s dt. And the equation, if the temperature kept constant, then the equation dA constant temperature is equals to minus p dvt as the constant temperature. dA delta A upon delta V at the constant temperature is equals to minus V, and if volume is kept constant, then the equation is delta A upon delta T at constant volume is equals to minus S. The change in work function for the complete process under isothermal condition can be calculated as follows. For an interstitial change according isothermal condition, equation may be written as dA constant temperature is equals to minus P dV. For a complete process under isothermal condition, when the volume change from V1 to V2, we will have delta A at constant temperature is equals to V2 minus V1 P dV. Putting PV is equals to nRT, that is nRT upon V for the n molecules of ideal gas, we get delta A is equals to T. Delta G is equals to uh, putting PV is equals to nRT, P is equals to nRT by V for n moles of ideal gas, we get delta A upon T is equals to V2 minus V1. From the integration V1 to V2 nRT by V upon dV, delta A at constant T is equals to nRT log of V2 by V1. Delta A at constant temperature is equals to W max. Variation of Gibbs free energy with temperature and pressure. The free energy is given by equation G is equals to T minus G H minus Ts. By definition of enthalpy, H is equals to U plus PV. Putting this value in equation, we get G is equals to U plus PV minus Ts. Complete the differentiation of this equation. dG is equals to du plus PdV plus VdP minus TdS minus S dt. D delta S is equals to delta Q reversible upon T is equals to du plus P dV upon T. TdS is equals to du plus P dV. Substituting these value in equation 4, dg is equals to du plus P dV plus VdP minus du plus P dP minus SDT, and the equation is dg is equals to VdP minus SDT. This is the important expression which gives the change in Gibbs free energy with change in pressure, and the change in temperature is a reversible process. Equation is a total differential equation. If a temperature kept constant, dt is equals to 0. Equation 6 has been formed. Dg at constant t is equals to V dp constant t, or dg upon dp at constant t is equals to V. If pressure is kept constant, dp is equals to 0. Equation 6 become dg at constant p is equals to minus s dt at constant p. dg upon dt as constant p is equals to minus s. The charge in free energy for a complex process under isothermal condition can be calculated as for the infinitesimal change. Use under isothermal condition, equation 7 may be as for a complete process use isothermal condition when the pressure changes from P1 to P2, we will have delta G at constant T, the integration from P1 to P2 VdP, putting the equation PV is equals to nRT, V is equal to nRT by P, and for the n mole of ideal gas, we get delta G upon T, P2 to P1 to P2 nRT by P upon dP is equals to delta G is equals to nRT ln P2 by P1. Further, the isothermal P1 upon P2 upon P1 is equals to V1 upon V2. Substituting the equation delta Z at constant is equals to nRT ln P2 by V1 is equals to nRT ln V1 by V2. This is the same expression for the equation 13 and 15 for the change in work function. Thus delta G is equal to delta A at constant T. This appears to be construction with the help of discussed in section 2.14. However, it is may be understood clearly equality hold good for the ideal gas but not in general. Criteria for the feasibility spontaneity of a process. As I already discussed in section 2.6 and 2.7, the net entropy change is the combined system and the surrounding delta S system is equals to delta S of surrounding plus delta S of system can be taken as criteria for the feasibility or the spontaneity of the process. The result arrived at were if delta S of system plus delta of S surrounding is greater than 0, the process is reversible, it is spontaneous for feasible. And the second, if delta S system plus delta S surrounding is equals to 0, the process is reversible, is system is in equilibrium. The above two result, delta S of system plus delta of surrounding is greater than or equals to 0, where the sign greater than refers to the irreversible process and the sign equals to refers to reversible process, which is the state for equilibrium. The above criteria, however, require acknowledgement of both delta S system and delta S surrounding, which is not convention. Hence, a number of other criteria with required knowledge of the charge in some thermodynamic quantity of the system only be referred for a infinitesimal process. The above criteria may be written as ds system plus ds surrounding is greater than or equals to 0, where the sign greater than stand for the irreversible process and the sign equals to for the reversible process. If the surrounding are delta Q reversible or isothermally at the temperature T, which may be observed by the system reversibly or irreversible, then ds surrounding is equals to delta Q reversible upon T. Further, according to the first law of thermodynamics, delta Q reversible is equals to du plus P dV. Substituting the equation ds surrounding is equals to minus du plus P dV upon T. Substituting the equation ds system is equals to minus du plus P dV upon T is greater than or equals to 0, or T ds minus du minus P dV is greater than or equals to 0, whereas ds stand for the entropy change of the system and subscript system has been omitted. In second, in term of entropy change of the system, the internal energy and the volume of the system are kept constant. Du is equals to 0 and dv equals to 0. Then ds uv is greater than or equals to 0, where the sign equals to is for reversible process and greater is irreversible process. The subscript u and pv indicate constancy of each other properties. Second, in terms of internal energy of the system, entropy and the volume of the system are kept constant, then the equation is 0 equals to or greater than dusv. In third, in terms of enthalpy change of system, by definition of enthalpy, we know that H is equals to U plus PV. Complete differentiation of this equation, dH is equals to du plus PdV plus VdP. Du plus PdV is equals to dH minus VdP. Putting the equation TdS greater than or equals to dH minus VdP. If entropy and pressure of the system are kept constant, ds is equals to 0 and dP is equals to 0, so that 0 equals to or more than dH which constant sp, where the equal sign is referred to reversible process and the sign greater than is equals to for the irreversible process. Fourth, in terms of change in work function of the system, by definition of work function, a is equals to u minus ts. Differentiating the equation, dA is equals to du minus tds minus s dt. TdS is equals to du minus SDT minus dA. Putting the equation du minus SDT minus dA is greater than or equal to du plus PdV minus SDT minus dA is greater than or equal to PdV. SDT plus dA is greater is PdV is greater than or equals to SDT plus dA. If temperature and volume of the system are kept constant, dt is equals to 0 and dV equals to 0. And the fifth is in term of free energy of the system. By definition of the free energy is by G is equals to T H minus Ts. H is equals to U plus PV. G is equals to U plus PV minus Ts. Complete differentiation of the equation dg is equals to du plus PV plus VdP minus T ds minus S dt. Du is equals to PV is equals to dg plus VdP and T ds. And putting the equation dg is equals to du plus pdv plus pdp tds minus sdt, and du plus pdv is equals to dg minus vdp plus tds plus sdt in the equation t. Putting the equation 6th, we get t 0 is greater than or equal to dg minus vdp plus sdt. Dg minus vdp plus sdt is smaller than or equals to 0 if the pressure and temperature of the system kept constant. dp is equals to 0 and dt is equals to 0. So we obtain therefore the sign of equal refers to the reversible process and greater than sign is for the reversible process. If dgp at constant pressure and temperature greater than 0, then the process does not occur if it is not feasible, and if the dg at constant pressure and temperature is smaller than 0, then the process is irreversible or not feasible. If dgp at constant pressure and temperature is equals to 0, then the process is reversible and the system is in equilibrium. Limitation of the criteria of spontaneity. No doubt the various criteria discussed above the helpful in predicting the spontaneity of the process, but they do not have tell anything about the following: the extent to which the reaction take place, the rate at which the reaction proceed, the mechanism by which the reaction proceed, advantage of free energy over an reaction proceed, advantage. An important advantage of free energy criteria over the entropy criteria lies in fact former require free energy changes of the system only entropy change it concerned with what is happening to the surrounding, whereas in the later entropy change criteria requires the total energy change of the system and the surrounding, that is for the change of the spontaneous delta S total is equals to delta S system plus delta S surrounding must increase. Gibbs-Helmholtz equation. The Gibbs free energy is given by equation G is equals to H minus Ts. Hence, for the isothermal process, we can write G1 is equals to H1 minus Ts1 for the initial state, G2 is equals to H2 minus Ts1 for the final state, G2 minus G1 is equals to H2 minus Ts1 minus H1 minus Ts1 is equals to delta G is equals to delta H minus T delta H. Delta G is equals to G2 minus G1 is for the free energy of the system. Delta H is equals to for the enthalpy of the system. Delta S is for the entropy change of the system. G is equals to U plus PV minus Ts. Differentiating the equation, dg is equals to du plus pdv plus vdp minus tds minus sdt. ds is equals to q reversible upon t is equals to du plus pdv upon t. ds is equals to du plus vdp. Substituting the equation, dg is equals to vdp minus sdt. dp is equals to 0 and dgp at constant p is equals to minus sdt. For the initial state, dg1 upon dt at constant p is equals to minus s1, and for the final state, dg2 minus dt at p is equals to minus s2. dg2 upon dt at constant p minus dg1 upon dt at constant p is equals to minus s2 minus s1. Del is equals to s2 minus s1 minus s2, and the given equation delta g is equals to delta h plus d up delta derivation of delta g upon delta t at constant p. This is the common Gibbs-Helmholtz equation. It may be noted that all form of the Gibbs-Helmholtz equation involve quantity like delta g and delta h or delta a and delta u, which are the state function and not depend upon the path followed. Hence, Gibbs-Helmholtz equation in general equation applicable on the as well as the reversible process application of the Gibbs-Helmholtz equation. One of the applicants of the Gibbs-Helmholtz equation is knowing the free energy changes at two different temperature and the enthalpy during the steady galvanic cell, which is briefly explained below. When a redox reaction is allowed to take place in a single beaker, heat is evolved. Earlier it was believed when the same reaction is allowed to take place in an electrochemical cell and electrical energy produced was equivalent to the heat evolved. However, later it was found that in Gibbs and Helmholtz by stating that the electrical energy produced was equal to the decrease in the free energy accompanying the cell reaction. They pointed out that n is the number of electrons given out by one two electrodes or taken up other electrode, then the quantity of electric produced, and F Faraday's F is equals to 1, F is equals to 96500 coulombs, and if E is equals to mf of the cell, then the electrical energy of the cell is mi is equals to nfe, and the Gibbs free energy is equals to minus delta G is equals to nfe. Substituting the values in the Gibbs-Helmholtz equation from the equation minus nfe is equals to delta H plus P derivation of minus nfe upon derivation of dt at constant P. Nfe is equals to delta H minus Tnf delta E upon delta T at constant P. Nernst theorem. W. Nernst in 1906 made a detailed study about the variation of enthalpy change, delta H, and free energy change, delta G of a system with decrease of temperature. The result thus obtained is Nernst heat theorem. According to Gibbs-Helmholtz equation, delta G is equals to delta H plus T at derivation of delta G upon derivation of T at constant P. From this equation, it is evident that the absolute zero, that is when T is equals to 0 and delta G is equals to delta H, unless delta delta G upon delta T is equals to infinite. However, Nernst observed that the temperature is lower toward absolute zero. The value of derivation of delta G upon derivation of T decrease then approach zeros asymptomatically. This means that delta G and delta H are not equally at the absolute zero, but the values of each other are mathematically expressed. Limitation T to 0 is equals to d delta G upon dt is equals to limitation d delta H upon T. Limit T tends to 0 is equals to 1. This is the graph which is given for the Nernst heat theorem. Third law of thermodynamics. It is the result of the Nernst heat theorem. It is enunciate in a general which has been called the third law of thermodynamics. In other words, third law of thermodynamics follow the more result of the Nernst heat theorem briefly explained below. According to the Nernst heat theorem, delta Cp approach 0 at 0 Kelvin. This implies that at 0 Kelvin the heat capacities of the reaction and product become equal because delta Cp is equals to Cp product minus Cp reactant. It seems most probable that at 0 K, all substances that have the same heat capacity on applying quantum theory to heat capacities of the solid, it is found that the heat capacity of the solid tends toward 0 at 0 Kelvin. Thus, Nernst heat theorem leading to the following result: limit T tends to 0, Cp is equals to 0. Also from Nernst theorem, limit T tends to 0, delta S is equals to 0. Proceeding exactly in the same way as above, it may conclude that the solid have the same entropy as absolute 0 of temperature and it tends towards 0 at absolute 0 of temperature. Limit T tends to 0, S is equals to 0. This generalization is known as third law of thermodynamics. It may be stated as the entropy of the all perfectly crystalline solid may be taken as 0 at the absolute 0 temperature. In a broader sense, the law is usually stated as follows. Every substance has finite positive entropy, but at the absolute 0 of temperature, the entropy may become 0. broader sense, every substance has finite positively entropy, but at absolute zero of temperature, the entropy may become zero. And in fact, it becomes zero in case of perfectly crystalline solid. Like the first, the second law, this law positive is also generalization based upon experience, and there is no direct proof of this application. However, the law has been verified in a number of ways. There is no doubt about the validity of the law. It is important to that third law of thermodynamics does not state the entropy is at zero at T is equals to zero. It merely states the all perfect like crystalline solid have the same entropy at T is equals to zero. This choosing a common value of zero. Importance of law evolution and absolute properties. The importance of the third law in the fact that the help in calculation absolute entropies of the element of chemical compound at desired temperature. The infinitesimal entropy change is ds is equals to delta q upon t, cp is equals to delta q upon t, so that delta q is equals to cp dt. Substituting the equation delta s is equals to cp dt upon t. Here is the integration, and then the equation is sr minus s0 is equals to 0 to t and cp dt upon t. Now, according to the third law of thermodynamics, s0 is equals s naught is equals to 0, st is equals to 0 to t, integration cp dt upon t, integration 0 to t and cp d ln t. Thus the substituting temperature can be calculated by the measurements of heat capacities at the number of temperatures, and this is the given graphs. Thus, the evaluation of the entropy requires the measurement of the heat capacity at different temperature down 0 K. However, a problem arises with the measurement of heat capacity at low temperature. For example, we plot a graph and the heat capacities are curve BC, the experiment values, and the point B corresponds to the lowest temperature up to the experimental values can be determined accurately to get the complete area under the curve. T to 0K exploration of the curve is then as shown by the portion B of the curve. The values corresponding exploited portion is usually found by applying Dewey third power law of the heat capacities of solid at low temperature, where A is the empirical constant, Cp is equals to AT cube. If B correspond to temperature T1, the lowest temperature up to which heat capacities can be measured experimentally, and C correspond to temperature T, temperature at which entropy is determined, and remembering that A is correspond to 0K. St is equals to 0 integration to T1 Cp upon T into dt plus T1 to T and Cp upon T into dt. The value of the first integral can be found by the substituting the value Cp from equation 4. We have 0 to T1 and Cp dt is equals to 0 to T1 a T3 upon T into dt. Sr is equals to a T1 cube upon 3 plus T1 to T and Cpt into dt. Further, as Cp is equals to at cube, therefore at1 cube upon 3 is equals to 1 by 3 Cp at T1. This means the entropy change from 0K to T1. This is equals to 1/3 of the value of Cp at T1. And the equation is Sr is equals to 1 by 3 Cp at T1 plus T1 to T2 integration Cp upon dt. It is important to remember that the calculation as described are applicable only a solid involving a polymorphic charge between 0 to T naught Kelvin. If some polymorphic change is involved in the range, the entropy transition is equals to delta H upon T, where delta H is the molar heat of transition and T is the transition temperature. We have included the calculated above. For the gaseous and liquid substances, the total absolute entropy of the substance of the given temperature will be the sum of entropy change that the substance has to undergo in order to reach the particular state, starting from the crystalline solid at absolute zero. Thus, in the substance is gas at 1 atm pressure and 25 degrees Celsius temperature, the entropy at the gas 25 degrees Celsius will be the sum of following entropies involved at different stages. First, the entropy of heating of the crystalline. uh, Second, the entropy of the fusion or fusion, the entropy of heating the liquid. Fourth, the entropy of vaporization. The fifth, the entropy of heating the gas. If the solid involve a polymeric transition, another has to be included in the above expression. Further, the first integral may be should given by the various entropy changes then occur in a temperature of substance are replaced by diagrammatically. This is the diagram for entropy change with the rise of temperature. Test of the third law of thermodynamic by calculation of equilibrium constant by comparing with entropies calculated from statical mechanics. Third, by proving that the different allotropic form of substance have equal entropies at absolute zero. Residual entropy, as explained above, entropies can be determined by applying third law of thermodynamics. These can be calculated from statical mechanics for spectroscopic data. It is about the most of the cases the agreement between the third law entropies and those calculated from statical mechanics is very fair. For example, standard entropies found third law and calculated from statical mechanics for CO and N2O are given below. The lower values of third law entropies are explained to the basic of at T is equals to 0 K, and the crystals of these substances are not perfect. That is, there some disorder present in solid even at T is equals to 0 K. Origin of residual entropy. To understand the origin of residual entropy, let us consider a crystal made up of AB molecule where A and B are the similar atoms so that the molecules have the same electrical dipole moment. These molecules can adopt different orientations such as AB, AB, AB or AB, BA, BA, AB. These arrangements are too many other random arrangement that the molecule can adopt very little difference of the energy. And then the calculation of residual energy. S is equals to K, L and W. W represent the number of possible orientation of the molecules that have the same energy, and W is for the thermodynamic property and K is the Boltzmann constant. Residual entropy of CO. Suppose a sample of consists of n molecules of CO, then the molecule are two orientation equally probably, that is CO, CO, OC, OC, CO, CO, OC. Therefore, same energy can be divided in two different ways. W is equals to 2n, S is equals to K ln 2n, K n ln 2, Kn is equals to R, S is equals to R ln 2 is equals to 2.303 R log 2, and the answer is 5.85 joule per Kelvin per mole. Residual entropy of FClO3. FClO3 molecule have four possible orientation with nearby. S is equals to RLN4 is equals to 2.303 R log 4 and the answer is 11.5 joule per Kelvin per mole. In general, if a molecule will adopt orientation at T where have the nearly the same energy, and residual will be SR is equals to R L and B. Thank you.